Hey everybody, today we will be solving some second order differential equations with circuits, all LRC circuits, one inductor, one capacitor, and one resistor in various configurations. And we're going to analyze the different response cases that we talked about in last video. So that is the underdamped, overdamped, and critically damped cases. So I've made these problems specifically so that we can see all of them. And let's get right into it. So in this first problem, we are going to find both the current and the voltage. And so I think the easiest thing to do first is to find the current. So we're going to apply our analysis of the negative portion. And we are going to find, so this is just a regular series configuration for RLC, the one that we use to derive the underdamped, overdamped, and critically damped scenarios for a series circuit. There is one for the parallel circuits, but this one is the easiest one. So, all right, so let's go ahead and see what this looks like. So at the negative infinity portion of this circuit, we just have an open circuit because, it's up at A. So right now we just have B right here. So this part right here, right, is going to be open because we're in a DC environment. It's a capacitor. And this part right here is that's the resistor right here. And right here is the inductor, like so. So 20 ohms right here. Now that's not really important because there's evidently nothing going through here. So our initial conditions are just 0 across the board, which is very lucky for us. We have no forced response when we go into the transient phase, so nothing is driving it. It's just going to start from the origin. So let's go ahead and do our positive portion of the analysis. And this time everything is on. So we're simply just going to copy this down and take this off, and we are at this position right here. Now I'm going to ignore the voltage right now because I want to find the current, because it seems like it's the easiest thing to find first because this is a loop. So let's go ahead and solve for I. So we've got negative 10 volts plus 20I plus 5I prime, right? Remember, because for an inductor, we have, to get the voltage, it's just the derivative of the current, plus, and we have 1 over, oh wait, actually, this is not supposed to be 1 over 3, this is supposed to be 15, sorry guys. That's supposed to be 15, and then we've got 1 over 15, and we've got this integral sign. Oh, but it's not 1 over 15. Remember, it's flipped, so we have to flip it again. So we've got 15 right here. T0 I d sigma plus V sigma equals 0. And we are going to find V of 0 plus prime, V prime 0 plus, because we need to know what that is to answer a second order differential equation. So 20I prime plus 5I double prime. Oh wait, not yet. That's solving it. I'm getting ahead of myself. We have to plug everything in. Negative 10 plus 20I 0 plus 5I prime 0 plus, which is what we're trying to look for, not V prime. That's for finding the voltage right now. We've got I prime 0 plus, and then plus, this is just 0 plus V 0 plus equals 0. And let's see, this right here is going to be 0 because we've got our good initial conditions here of just 0, so we can just cancel all of these guys out. And we're going to be left with 5I prime 0 plus equals 10. And so simplifying that down, we get 2 amps per second, okay, because it's a derivative with respects to time. Nice, nice, nice. So we're going to hang on to that. The next thing that we're going to do is step 3, and we're going to take the derivative of this differential equation, or yeah, this equation, and we're going to get, let me write it down. We're going to get 20i prime, what I was doing earlier, plus 5i double prime, plus 15 just I, right, because the antiderivative of this is just going to be the integrand, equals 0. Divide everything by 5, I double prime plus, what is that, 4i prime, plus 3i equals 0. And then we're going to apply the characteristic equation for this. I like to use R. My professor used S. I'm sure some textbook uses something else, but I'm going to say R squared plus 4R plus 3. And this is to solve the homogeneous equation. So right now, this is homogeneous, so the answer will be the homogeneous equation, but typically when you're finding the homogeneous equation for the second order differential equation that doesn't have any time dependencies right here, you're going to use a characteristic equation. So I of t is going to equal something, and this is how we're going to solve it. So that's going to equal 0. We've got r plus 3 and r plus 1. Didn't even have to pull out the quadratic equation for this, because, yeah, r squared, r3, yep. And we will get r is equal to -3 or -1. So we've got our two roots, and these are going to attribute to the solution, which is going to be in the form, hopefully you remember, but the form with real roots, it's going to be I of t is equal to k1, some arbitrary constant, e to the -3t, because that's our first root, plus k2 e to the -t, right, -1t. And to find k1 and k2, we're going to need the derivative of the solution. So we're going to get -3k1 e to the -3t plus, or minus, I should say, k2 e to the -t. And when we set all of this to the initial conditions, we know that I of 0 plus is 0. I of 0 plus is 0 equals k1 plus k2, correct? And then I prime of t is 2. Okay, so we've got 2 is equal to -3k1 minus k2. And you can solve this out by hand, or you can use a calculator, but I've already solved these out. And we get that k1 is equal to -1 and k2 is equal to 1. And so we get an answer if I of t is equal to -e to the -3t plus e to the -t. And this is the solution for the current. And remember, the current is going this way. It is going clockwise. All right, now let's go ahead and solve for v of t. So I'm going to solve for v of t on a separate page, but essentially we're going to have the same initial conditions. So there's actually two ways to solve this. There's an easy way and there is a circuits way. And we're going to do the circuits way first, just so that we can see if we can derive some intuition of what's going on. So let me just write down our initial conditions, because these aren't going to change. The first thing that we're going to do is actually we're going to do the circuits way. So in the circuits way, we are going to find I in terms of V, right? I in terms of V. And the reason why we're going to do this is because, remember, we are trying to solve for a nodal analysis so that we can get our voltage, okay? So I'm just going to go ahead and repaste this right here. Instead of finding the current, we will have v of t right here. And so the idea is that we want to get the current through here, and we want the current through here. Now, the question is, how do you write this in a current form? Well, you really can't, or at least I don't know how to. So instead, what we're going to do is we're going to walk up from here and here and here using the regular convention of the I that we found. And we're going to get negative 10 plus 20i plus 5i prime, right? Because, so we're basically taking half of the loop analysis because it's just easier. Plus v is equal to 0 because this is v right here, and we can call it whatever we want, and we called it v. So we're going to get everything in terms of v, and so we're going to get 10 plus minus 20i minus 5i prime. And then we are going to use KCL. So KCL like normal, okay? Or step, I guess we'll say step 1. Use nodal analysis, okay? And we're going to apply a nodal analysis at that node right there. So we've got N1, and we've got V, right? But technically we're not going to solve it in that way because we'll just have it straight up because that's all we've got. We've got the IC right here, the I capacitor, or I2. Actually, let me just call it I2 just so that we don't confuse anybody. And then we're going to say plus I1 is equal to 0. But here's the thing. We just denoted it to being this way, right? This is the actual physical interpretation, but the nodal analysis calls for us to do it this way. So this is actually going to have to be minus I1 right here. And so we get that I1 is equal to I2. And we found, and so we can simplify this further because we know what I2 is. I2 is just the capacitor, which is going to be 1/15 V prime. And guess what? We know what V is, right? Well, we don't technically know what V is, but we can get it in terms of. And so we are going to have to find the initial condition for V prime 0 plus, okay? Because we only have I prime 0 plus, but we need a V prime 0 plus or else we can't solve this, right? And so we're going to take the prime of both sides, right? And we're going to say I 0 plus prime, not prime, sorry. We're going to take the 0 plus of each side is equal to 1/15 V prime 0 plus. And we know what I 0 plus is from earlier analysis, and that's just 0. So V prime 0 plus equals 0. So now we can move on, okay? And we can move on. We can actually move on because we said that we know what I1 is, and this guy right here is I1, okay? So we can just plug in 1/15 V prime into all of these I1 spots, okay? And so we're going to say V is equal to 10 minus 20I, which is 1/15 V prime plus 5 times 1/15 V double prime, because we're putting it in here and it's been primed again, equals V, okay, because from here. So basically what we're doing is we're just plugging in this guy into here, right? Okay. And so now we actually have everything in terms of V prime. We have our initial condition for the derivative, and now it's just a matter of solving it out. So let's go ahead and do that. We will get 5/15 V double prime minus 20/15 V prime plus 10 is equal to V, right? But we're going to move this because we don't like that. That's going to equal to negative 10. I think I made a mistake. Oh, I see. This is supposed to be a minus right here. Yeah. And then we're going to add all of this to this side, so it's all plus right here. It's plus like that. And then on this side, it's still 10. Yeah. Oops. That was an algebra mistake. Okay, so all of these guys are going to simplify down to v double prime over 3 plus 4v prime over 3 plus v is equal to 10. Multiply both sides by 3. And we get v double prime plus 4v prime plus 3v is equal to 30. And right now you're supposed to be excited because look at that. We've got our homogeneous differential equation. So step 3, or step 2 rather, we're gonna solve, okay? And we get our characteristic equation, right? Plus 3 equals 0, and that's gonna have roots of -3 and -1. And then, but this time we actually have a particular solution, so we know that VH is equal to K1 e to the -3t plus K2 e to the -t, but VP is equal to K3. And we're going to plug in K3 into this equation right here, and we're going to get 3K3 is equal to 30, and K3 is equal to 10. And so when we go up here, I'm going to say solve, and what we're going to do is we're going to have this v of t, which is the whole solution, is equal to 10 plus K1 e to the -3t plus K2 e to the -t. And v prime of t is going to equal to -3K1 e to the -3t minus K2 e to the -t. And when we plug in our initial conditions, we saw that our initial conditions were 0 and 0 for voltage. So we just get 0 equals 10 plus K1 plus K2. 0 equals -3 K1 plus minus K2. And when we solve this guy out, we're going to get that K1 is equal to 5 and K2 is equal to -15, which is V of t is equal to 10 plus 5e to the -3t minus 15e to the -t. And that is the solution. Now, the easier way of doing it is actually the math way. So, math way. And you may have figured this out already, but you could literally just get this guy right here, our nodal analysis, and just say it, right? We have, and the math way only works if you had found I of t first. So you're going to say, oh, let me make my nodal analysis. I'm going to have 1/15 v prime in this first branch right here, and then I'm going to have -I in the next branch because that is I right here, which we found right here. So technically we're going to have to copy and paste this, move it right here just so that we have for reference. -I equals 0, and then we're going to have 1/15 v prime equals I. And what we're going to have to do here is we're going to have to integrate so that we can get v. So we're going to integrate both sides with respect to dt. Okay, so a general integration. And we're going to say 1/15 integral of v prime is just going to be v, and I is -e to the -3t plus e to the -t dt. And hopefully we remember how to integrate, and we're going to say from 0 to t actually. So so that we're mathematically correct right here. And remembering to integrate, we're going to take this guy down and get the reverse of it. So we're going to say 1 of 3 e to the negative 3, and it's this sigma guy, and yep, it's the sigma guy minus e to the negative sigma guy, and then we're going to go from t to 0, and we got 1/15 v, and we're going to plug this in, 1/3 e to the negative 3t minus e to the negative t, and then minus 1/3, and we're going to get this guy right here is going to equal to 2/3, so positive 2/3 right here, so 2/3 plus 1/3 e to the negative 3t minus e to the negative t equals 1/15 v. Multiply everything across by 15, and lo and behold, we get 10 plus 5e to the negative 3t minus 15e to the negative t. Or you could just solve out the general form. You don't have to put these guys in yet, and then just use the initial condition right here. All right, so that's solving one of them. And if you guys were paying attention, this is actually the overdamped case because the roots are real, and so the general form of this, and you don't have to like plot it like for exactly, but generally it's going to look like this, right? Where this E, we have this E envelope, and it doesn't touch it. The critically damped case does touch it, like this or like that, but this is underdamped, and so there's no dance that's allowed to happen, no waviness. Okay, here's the second one, guys, and this one we're only going to find voltage. So let's go ahead and start with our analysis. We have step 1, negative infinity to 0, and we have the switches being open, so basically our circuit is going to look like this right here, right? This is going to be open right here, and this is just going to be some wire, and this is going to be open because it's a capacitor, and we've got our resistor here. Doesn't really matter. Once again, our initial conditions are just 0. And so let's go ahead and go into step 2 so that we can find our V prime of 0 plus, and then the corresponding transient equation. And we are going to have everything turn on this time. So now everything is alive. Best thing to do, apply a nodal analysis. So for our nodal analysis, we're going to say we've got V. Now, the question right here, what are we going to do right here? Well, we want to find V, and we know that we have to go up 4 volts and up VL volts. So this branch is going to be defined as VL plus 4, but we can only apply that equation to the inductor. So we're going to say VL is equal to V minus 4. So we will have 1 over 12, 0t, and V minus 4, d sigma, plus I sigma. And right here is very easy. 1 over 48, V prime, and finally V over 12. Now our job is to solve for V prime of 0 plus, and V prime of 0 plus is simply just going to be 0 plus I of 0 plus plus 148. Sorry, that's actually all equal to 0, because right here we get our v prime of 0 plus right here, and plus v of 0 plus right here. And once again, all of these guys are 0. And so this time, v prime of 0 plus is equal to 0. So step 3, let's apply a derivative to all of this to get rid of that nasty integral right there. And so we're going to take the derivative, say 1 over 12 v minus 4, everything in integrand stays, plus this guy dies, plus 148 v double prime plus v prime over 12 is equal to 0. We're going to multiply everything by 48. We're going to get v minus 4 plus v double prime, 4 times v minus 4 plus, same thing here, 4v prime equals 0. And we will get v double prime plus 4 prime plus 4v is equal to 16. And when we solve this guy out, we are, of course, going to use the characteristic equation. Solve for step 4. And the cool thing here is that we are going to have a homogeneous, and we will have to use the r squared for this to find the homogeneous, and then r squared plus 4r plus 4 is equal to 0. And we've got r plus 2 squared, right? This is one of our known square things, and so we actually get that r is equal to r, which is equal to -2. So we're going to have it in the form of k1 e to the -2t plus k2 t e to the -2t. I know a lot of people like to distribute these guys out. I personally don't, because we're going to take the derivative of this, and it's just easier for me to look at when they're together. I mean, when they're distributed out. All right. Now we've got to find the particular solution, which is going to be Vp equals K3. And that's just going to be 4K3 is equal to 16. And so we get K3 is equal to 4. Now we know what our full V of t is going to look like. It's going to look like 4 plus this guy right here, K1 e to the -2t plus K2 t e to the -2t. We can actually solve for K2 right here, K1 right here, because when we plug in 0, this term cancels out. So we're going to get 0 is equal to 4 plus K1, and so K1 is equal to -4. And then we are going to find the v prime of t so that we can actually find K2, and we're going to get -2 K1, which is just -4, e to the -2, e to the -2t, plus we're going to have to use the product rule right here. So we're going to hold the t constant and take the derivative of e to the -2t. So we're going to be left with -2 t e to the -2t, plus now we're going to take the derivative of t and hold e to the -2t constant. And we're going to say that that is e to the -2t right here. And so we're going to go ahead and plug in zeros all around. So we've got 0 right here, and we are going to find that this guy becomes 0 right here. This guy becomes 1 right here, so we have 1 K2, so that's a good thing that our K2 didn't go away. And we've got K2 is equal to 8. And so our final answer for this problem is going to be V of t is equal to K1 e, or not K1, we've already found that. It's going to equal to 4 plus 4e to the negative 2t plus 8t e to the negative 2t. And this is our answer. Now this is a critically damped situation in which the frequency or the oscillation is going to just tap this time e to the negative 2t, right? And it's going to look something like this, not exactly. It's going to tap it at one single point and then it's going to die out. That's what that one will look like, generally. Okay, let's go ahead and do our last problem. All right, so here is our last problem. Yeah, let's just get right into it. We're supposed to find v of t right here. So once again, like normal, step one, we're going to do an analysis on the negative time frame, and we will see that it's at position A at first, position A, and we're going to go ahead and find our initial conditions. So I of 0 minus is equal to I of 0 plus, and that's simple. We're gonna pretend that the current is being pushed this way. So it's gonna be 8 divided by 4 is 2 amps, and V of 0 minus is equal to V of 0 plus across this capacitor guy right here, or yeah, for this V that we want. Now notice something very interesting. The inductor creates a short up to V, okay? So I'm not even going to consider this 6-volt battery right here because this is ground now, okay? Now that the inductor had failed, it is ground now. So this is just 0 volts. Now we're going to look at the transient analysis in real time. This time we are going to be in position B, and we're going to have the 12-volt battery right here be the driving force. We still got this 4 ohms right here, and we've got this inductor alive, and we've got this capacitor here and a battery, 6 volts. This is 1/4 farad. We're going to apply a nodal analysis. We're going to say V minus 12 over 4 plus, we've got an integral again, 1 over 6, 0t, V of sigma plus I of sigma, plus, now we've got 1/4 right here. And I'm going to write this in dt because to get to V, right, we're going to have to say VC plus 6. This VC right here, that's the thing that we're going to have to analyze with our differential equation. And so we're going to get V is equal to VC minus 6. And so it'll look like this. Now we're going to go ahead and find V prime 0 plus, because we still need that. So we're going to say everything is V of 0 plus over 4 plus 0 plus I of 0 plus 1/4 V prime of 0 plus is equal to 0. Now we saw that V of 0 is 0, but I 0 plus has a value, so this is going to be 2 right here. This is 2. This is 0. We're going to get -3 right here. Actually, an easier way to see this is we're just going to multiply everything by 4. We'll get -12 right here, plus 2 is equal to V prime. Oh, that's not 2. We multiplied everything by 4, so that's 8. We get V prime is 0 plus, and we get V prime 0 plus is equal to 4 volts per second. And then finally, we're going to take the derivative. So we're going to take the derivative of everything, and we're going to say we get v prime over 4, because this right here is just a constant, so we can not consider that, plus 1/6 v plus, that gets canceled, 1/4 v double prime, and we don't care about the 6 because that gets taken out. 1/4 v double prime is equal to 0. We are going to multiply everything by 4, v double prime plus v prime plus 2/3 v, because 4 over 6 is just 2/3, and that's all equal to 0. Now we are going to apply a characteristic equation to this, so that thankfully it is homogeneous already, so the homogeneous solution is going to be the answer to this. So we're going to have step 4, and that's solve, and we're going to get the characteristic equation of r squared plus r plus 2/3 is equal to 0. We are going to use the quadratic equation for this, and then a calculator. We get that b is -1. Sorry, negative b is 1. Well, wait. This b is 1, so negative b is -1. b squared is just going to be 1 minus 4 times 1 for a times 2/3, which is c, over 2 over a, which is times 1. And simplifying this down, we're going to get -1/2 plus or minus j root 15 over 6. So now we know that our solution is going to take the form of k1 e to the negative alpha t, which we found that alpha is going to be 1/2. So this is alpha, and this is beta. And notice that this j is just denoting that beta is different from alpha. Okay, we're trying to encode more information so that we can describe holistically what is happening. And so we've got the t right here, cosine of root 15 6th t plus k2 e to the -1/2 t sine root 15 6th t. Now we're going to plug in a 0 so that we can actually find k1. And we found that the initial condition is 0. And sine of 0 is just 0, so the k2 gets removed completely. So we've got k1 e to the 0. So k1 is actually 0. So the cosine term of this function gets canceled out. So the real equation is actually just the sine portion. That being said, we're still going to have to take the derivative so that we can find k2. So v prime of t is equal to k2. Now, remember what's going on here, doing the product rule. We are going to take the derivative of the e first and hold sign constant. So we're going to say -1/2 is e up to e to the -1/2 t sine root 15 6th t plus, now we're going to hold the exponential constant, and we're going to take the derivative of sine, and using chain rule we're going to take out the root 15 6th, and that's going to become cosine root 15 6th t times, I'll put it right here, e to the -1/2 t, like so. And then we're going to plug in 0, and we found that v prime of t is actually equal to 4, and so we're going to say 4 is equal to k2, and remember, anything that's 0 in sine just becomes 0, so we're just going to have a big fat 0 right there, plus, and this guy is going to stay 1 right here, and so we're only left with root 15 over 6ths, and we get k2 is equal to 24 root 15. And so our final solution is 24 over root 15 e to the negative 1/2 t sine root 15 sixths t. And that is the solution. All right, guys, that's going to be it for differential equations. I may consider posting another video later on with a lot more questions, and hopefully I'll have solutions for that, but I have to write them, so it's going to take a bit. In the meantime, we are going to be going to the final unit of introductory circuits, and we are going to continue looking at inductors and capacitors, but this time we're going to try to see a little more than just one or two inductors, and we are not going to consider the transient phase anymore, but we are going to go into a completely different system, a different transformation, if you will, where we don't analyze in the time domain, but a very double E or electrical engineering topic is to transform all of these circuits into the frequency domain. Okay, and so we're going to solve all of these problems in the frequency domain. We aren't going to find the transient form anymore for the rest of this, but if you ever, this could be definitely useful in circuits where you need to make sure that you consider what's going on in like minute periods. Okay.